All right, so we're getting into exponential functions. And this is 4-2, so let's go ahead and get it. All right, first thing about exponential functions is expressing exponents. So you can express any exponent in two ways. You can express it as an exponent or a radical, radical. Right, so you can say this is, maybe we would call it a rational exponent. So like, in this example is a to the m over n power, which is going to be the same thing as, or I'll say equal. You can interchange them. The nth root of a to the m. That's how I would write it. I see how they write it a little different. I prefer to write it this way. All right, so that's one thing, right? And then a couple other things about exponents. Let's see if that talks about it. I'll just bring it up. So first, or after that, anything, and a to the 0, right, is equal to 1. So, if I have anything to the 0 power equals 1. No matter how complicated it looks, if it's all to the 0 power, it just equals 1. And then another thing is if I have a to the negative 1 power, or maybe I should say negative n power, then that's equal to 1 over a to the positive n power, right? We don't consider mathematics fully simplified if you have a negative exponent. So you would rewrite it. And then kind of the same idea. Like let's say we have like b to the second over, a to the negative third. And what is that equal to? Well, a lot of people always just say like, oh, you flip it if it's negative. But you got to be careful with how you think about it. You don't just flip it. Because the a is the one with a negative exponent, not the b. The b's fine, so I don't want to flip it. I would put the a, that was supposed to be an arrow, but whatever. I put the a in the numerator and make the exponent positive. So it would be a to the third, b to the second, right? Or I'll give you one more of those. If I have like x to the third, y to the negative, fifth, z to the, first, that's equal to x to the third, z to the first, but then y, since it was negative, it goes to the denominator and becomes a positive 5. So when they have a negative exponent, you can move it to the numerator and make it positive if it was in the denominator. Basically, wherever it is in the numerator or in the denominator, if it has a negative exponent, you move it to the other place and make the exponent positive. All right, it doesn't make the value of a negative or positive. It just makes the exponent positive. So we'll kind of, hopefully you'll be able to get down with me on that. So additional properties of exponents, you're going to need to know about the properties of exponents. But I'll tell you kind of as we get into it. So what is an exponential function? Or let's just do some evaluating some exponentials. All right, and then we'll start talking about what an exponential function is. So first, if I have f of x is equal to 2 to the x power, and I say find f of negative 1. Find f of negative 1. So I'm going to say this is f of negative 1 is equal to 2 to the negative 1 power. Now, this is what we just talked about, right? So this would be equal, because I can think of any number, like a fraction, and say, okay, right now it's in the numerator, but it has a negative exponent. that means I need to take it and put it in the denominator and make the exponent positive. So what would be in the numerator? Well, you can say anything's times 1. So the 1's still in the numerator because I could say 1 times that, right? And it'd be the same thing. So the 2's in the denominator now, and the exponent is positive. So that's just 1/2. So this thing equals 1/2. All right. What about, f of 3? Well, that's equal to 2 to the 3rd power. Exponent's positive, we're all good. That's 2 times 2 times 2. I'll write it. 2 times 2 times 2, which is 8. So this is 8. Okay, what about the 5/2? So f of 5/2. What is that? That's 2 to the 5/2 power. Now, maybe that makes sense to you, maybe it don't. For me, it doesn't make a whole lot of sense. Now, you could put it in your calculator, and maybe your calculator would give you an exact answer, which is what we're looking for, or maybe it would give you a weird decimal, which is what we're not really looking for. So my advice is to instead switch it to radical form and say, okay, this is, the the square root. Well, I'll put a square there too. Most of the time, if it's a square root, you don't see a 2 right there. It's just understood to be there. Of 2 to the 5th. Well, how do I simplify that? Well, I know that that's just, the square root. I'm going to write it without the radical this time because it's understood that way, right? This 2, without the index is what it's called, the index, is understood to be there. So, right here is understood. Right? If you see a square root, it doesn't normally have a 2 there. You can put a 2 there if you want, but it's kind of like if you see an x, you don't normally see a 1 times the x because it's understood that if you see an x, there's a 1 there. Or you don't see a 1 in the exponent on that x, right? But it's understood that it's there. Same thing. All right, so this is really 2 times 2 times 2 times 2 times 2, right? That's 2 to the 5th. And we know that square roots, for every number that I can have 2 of, I can bring them out. So I can bring this out, and I can bring that out as 2 times 2. For every pair, I can bring one of those out. So I have 2 pairs, so I can bring a 2 out for one pair and a 2 out for another pair. And then I'm stuck with the leftovers as a 2 in there. So this gives us 4 square root of 2. This is the exact, right? If you put it in your calculator, you're going to get an approximation. Approximations are nice, but exact is better. All right, now, what about if you see, f of 4.92? This is where approximations are very nice because I don't know what, that's 2 to the 4.92 power. I can say 2 to the 5th power is 32. 2 to the 4th power is 16. So it's very close to 32. I don't know exactly what it is. This is where you just put it in the calculator. All right. I'm not going to worry about doing that. I'm assuming you know how to do that. If you don't know how to do that, talk to me in class because I can't get the calculator up here. All right. So let's keep it moving. All right. What is an exponential function? So basically you have, a to some power, right? That's kind of I'm not really going to say like parent function. You can think of it like there's really 2 models of exponential functions. There is the growth model. Growth. Right, this is exponential growth. And is this going to show it? All right, yeah. And then there's like growth. Really, is exponential growth when a, the absolute value of a. I'm going to just say a. When a is greater than 1. And then you have exponential decay, exponential decay when, you know, A is greater than 0 but less than 1. So exponential growth looks like, growth is like this. It's going up, right? Exponential decay is like this, going down. All right, so this is showing us the growth model. So it's showing us, right, 2 to the x power. So since A is greater than 1, this is growth. All right, and you just plug in some points, right? Yeah. There's 3 points that you can always count on. I mean, there's more points you can always count on, but if you have A to the x power, then you can have this point -1, 1 over A, the point 0, 1, and the point 1A. That's kind of the classic points that you can get. You can get more points, obviously, in this table. You get more points. Yeah, so when A is greater than 1, this is the growth model, which means it's increasing. It's also continuous, and its domain is from -infinity to infinity, right? Domain, -infinity to infinity. Range, 0 to infinity. Why 0 to infinity? All right. Well, if I have a positive number, all right, so if A is positive, and I put any power is always going to equal another positive number. It's never going to equal a negative number. And it'll never equal 0. Maybe I'll say never because there's 2 things. So never equal, or I'll say equals a positive, never equals 0, equals a positive every time, and it can never equal 0. Why can't it ever equal 0? All right, let's think about it. I'm gonna do some scratch work right here. Let's say 2, and then we say like to the -100th power. All right, well, that's just 1 over 2 to the 100th power, which is just going to be 1 over a really big number. Really big. That's not even how you spell really. Really big number. All right? Which will be close to 0, but it'll never equal 0. What about 2 to the, 500th? That's just going to be, 2 to the 500th power, a really big number. Not close to 0. What about 2 to the 0 power? Haha, what about that one? Sir, what do you say about that? Well, I say 2 to anything to the 0 power is 1. So therefore, it will never be 0, and it will never be negative, which means it's always positive, right? 0 is not a positive number. All right, therefore, it has a horizontal asymptote at the value of y equals 0. So this is, of course, thinking about kind of the parent function, right? Exponential functions are a little different than, polynomials or some of the other functions we've worked with. For an exponential function, you kind of treat each individual exponential function like its own parent, or that's the way I look at it. Like, the parent in this one is y equals 2 to the x. But another parent would be y equals 3 to the x, or y equals 4 to the x. They all look about the same, but, it's kind of like a little different. There's not, the stretches and compressions aren't, it's not about stretches or compressions in this. It's just about like this is 2 to the x, this is 3 to the x, this is 4 to the x. They all kind of look similar, but they're not exactly the same. So I kind of treat them all like their own parent functions. You just look at the simple version of it, and you'll see what I'm talking about. All right, now we have, here, A is, less than 1, but it's greater than 0, right? So this is decay. This is the decay model. It's decreasing over time. And you see these points that pop up, and you see, still has a horizontal asymptote at y equals 0. Domain and range is still the same, but it's just the graph, instead of going up from left to right, it's going down from left to right. All right, and you still have the same points as before it goes through. So it's just the trends, right? When this is 1/2 and that was 2, right? Exponential growth, exponential decay. They look very similar, but they're not. Check out the differences. All right, so this is why I kind of consider each one its own parent. So the 10, you see how similar they are, but they're not the same. And then you can look at the same colors. You see 10 to the x power, or 1/10 to the x power. We have, decay models on this side and growth models on this side, right? Decay means the a value is greater than 0, but less than 1. And the growth means the a value is greater than 1. Oh, yeah. There it is. There it is. Yep. The function is decreasing, whereas the function is increasing. The domain and range of all these are the same. All these have a horizontal asymptote on the x-intercept, or the x-axis. Horizontal asymptote at y equals 0, right? Okay. So characteristics. Now here it says graph and then give the domain and range. I don't have a nice graph out, but that's okay. I'm just going to sketch one like this. Now, you're going to be tempted to just jump in your calculator. I know you are. And that would be an unwise move on your part. All right? Because then you're not going to learn the things you need to learn to be successful. So let's instead go to a table to begin with. Right? So we're going to say we have the x and then we have the y, or f of x, right? And this is a very basic. It's just the little, parent function of this 1/5. If it was other things happening, like I'm adding something, then the transformations are getting in there. So I'm considering this like the parent function because it's the most basic version. And I'm picking some x values. Now, the x values you can always pick would be the -1, the 0, and the 1. The -1 is always going to be, you flip that, right? So it'll be 5. The 0 is always going to be 1. And the 1 is always going to be, whatever the a value is. All right. Now, let's make sure you understand that. So let's pick, negative, I'm going to say -2. And let's pick +2. So think about what this is saying. If I have 1/5 to the -2 power, well, now that's the same thing as 1 to the -2 power over 5 to the -2 power. Well, we just talked about negatives, and since it's negative in the denominator, the 5 is negative in the denominator, I need to bring it to the numerator, make it positive. But the 1 is in the numerator, and it has a negative, so I need to take that to the denominator and make it positive. So that becomes 5 squared over 1 squared, which is 25. Over 1, which is 25. So that's that point, 25. And then down here, right, this is 1/5 squared. Well, that's just 1 squared over 5 squared. Hey, it's all positive there. We're good. That's 1 over 25. So, if we graph this, I got, I'm going to say this is 1, this is 2, this is -1, this is -2, and, we'll call this 1, that's -1. All right, so I have this point, 0, 1. That's my first point, or the first point I'm plotting. Then we got this point, -1, 5. So my graph, let me erase my graph Sorry, guys. That's why we work in pencil. I know some of you got that pen and you're like, this guy. But I've been telling you this stuff for years now, bro. I've been telling you this your whole life. You still ain't listening. All right. 1, 2, 3, 4, 5, 6, 7. All right. First point, 0, 1. Now, second point, -1, 5. So, right here. Then we got 1, and then 1/5. So, like, right there. And then 2 would be 1/25. So, like, basically 0, but I can't even get it that close to 0. I mean, it's not 0, but it's very close to 0. And then this up here is so high up there that, we can't do it, the 0.125. So this graph is looking like this. And then domain, well, from -infinity to infinity, right? Because it goes left forever and it goes right forever. Range, well, it goes to 0. Can it equal 0? No, can never equal 0. So 0 is the smallest it can be, but it can't be 0. It can just get infinitely close to 0. So we put the, not equal 0, right? Parentheses. And then to infinity because it's going up forever. Let's say increasing, decreasing intervals. Is it increasing? If you read it from left to right, it's always decreasing. So none is never increasing, and it's always decreasing on its entire domain. So from -infinity to infinity. All right. Let's do another one. All right. Graph each function. So look, this is for comparison. This is your parent. And then we look at this. Well, what's happening there? What's that negative do? Remember, things that happen inside the grouping with the x, well, you might be thinking, well, where is the grouping? Well, x is in the exponent. So things that's happening in there when in the exponent position with x, they affect x. Things that's happening outside of that, they affect y. So outside meaning not in the exponent position. They affect y. So this affects y. So if my y values become negative, well, this point right here, this point right here that would be 2, 4 becomes, this point right here, 2, -4. And this point right here, which would be right there, and then this point right here would be right there, and, this point right here would be right there, and if you did that enough times, you'd say, and then hopefully you'd say, this is a reflection. Reflection on, not your y-axis. People get that confused because they're like, well, it affects your y values. It does. But when you flip them, right, when you change your y value from negative to positive, it reflects on the x-axis. That's actually a y value change. And then domain and range. Well, domain from -infinity to infinity. Range, well, from 0. Oh, I'm sorry. We got to do this in order from least to greatest. We start at the bottom and we work our way up. -infinity all the way to 0, right? That's the range. We're talking about for the green graph, not for the red. All right. Increasing, decreasing. Increasing interval, decreasing interval. I'm just adding that because that's a good thing to add. Is it increasing? No, never, none. Is it decreasing? Yes. If I follow this graph forever, it's always decreasing. So my domain from -infinity to infinity is decreasing. Oh, now you see the grouping, right? What does this mean? It's grouped up with the x. Remember, x is like whatever's happening to it is the opposite of what it looks like. So x plus 3, that looks like it's adding 3 to the x, but no, it's actually taking all the x's and, all the x values and subtracting 3 from them. So all your x all your x values, you're going to subtract 3 from your points, and you're going to have the graph is shifted left 3. So that means, you find a point, this point here, this point here, this point here, this point here, and you shift it to the left. 1, 2, 3, right? 1, 2, 3, right? 1, 2, 3. 1, 2, 3. Now we got our new points. This piece, this piece, this piece, this piece, right? You can take, this point right here if you want to, but since that's 1, that's 2, that's 3, and then you graph, right? You see that it's so shifted to the left. What does that change for domain? Nothing. It's still going left forever, so from the negative infinity, and it's still going to be going right forever to positive infinity. What about the range? Well, it still can't be 0. 0 is the smallest it can't be. It can be infinitely close to 0, and then it's going up forever. And then this is increasing, so increasing on, from negative infinity to infinity. Right, so hopefully all your work on transformations is working out now, and you're like, oh, I see it. It makes sense. All right, what about that? So hopefully you can still, I'm not making tables. I used to make the tables, but I feel like we're getting more advanced now. We should be familiar with what's going on. So let's think about this. This is the parent function. Right, this is my parent. This is what's graphed up there. Now I know that this is moving the graph right to, and this is happening outside the x values, right? Not with the x values, so it affects the y values. And I'm subtracting 1, so this is down 1. So every point that I would have, this point, any point, this point, right? This point, I like to get points that are clear, but wherever is going to the right 2, 1, 2, and then down 1, down 1. So to the right 1, 2, and then down 1. To the right 1, 2, and then down 1. To the right 1, 2, and down 1. To the right 1, 2, and down 1. Ho. Look, maybe you need another one right here. To the right 1, 2, and down 1. So now I see that it's like this is the line that I can't. Something like that, right? Because this point right here would go to the right, down over 1, 2, and then down 1 right there, right? This one right here would be right 2, down 1 right here. So now I'm seeing that before, the y value, or y equals 0, was my horizontal asymptote. But when I shifted it down, this line right here becomes my horizontal asymptote. Y equals -1, right? Because of the downward shift. So what's my domain? Still from negative infinity to infinity. What's my range? That's from, would be -1, but I can't equal -1, and then to infinity. So -1 to infinity, parentheses, because I can't equal -1. This function is increasing, so it's increasing along its domain, negative infinity to infinity. All right. So what would you do when there was no graph, right? Maybe this is when you're like, okay, every other one you showed me a graph first. What about when there is no graph? Well, you can just graph the parent function if you prefer, and then shift it, all right? So that's what I'm going to do. I'm going to think about the parent for all these, right? So that's just y equals 1/3 to the x power. Maybe you need to plot a couple points, but if you kind of remember the idea of just the 3 points, right? The point -1, 0, and 1, you can get what you need. But you can also just keep plotting. So -1, if 1/3 is to the negative power, it flips. So this is 3. 0, so 1/3 to the 0 power, anything to the 0 power is 1. And then 1/3 to the first power is 1/3. So if I plot these 3 points, -1, 3, 0, 1, 1, 1/3, that probably gives you everything you need. And you can say, oh, I see that this is the decay function. You know, it has a horizontal asymptote at y = 0, and then it's going up like this. So this is the parent. So, you know, how would I graph the other ones? You just look at their transformations. Shift them, right? Shift them left, shift them right, shift them up, shift them down. We'll do 52, right? It says +4, so that means every point just goes up 1, 2, 3, 4. This point right here, 1, 2, 3, 4. This point right here, 1, 2, 3, 4. Right? Every point. And that means that my horizontal asymptote is no longer at y = 0. Now the horizontal asymptote at y = 4. So domain and range, domain. This is for 52, from -infinity to infinity. Range from 4 to infinity, right? So the shift up and down affects our horizontal asymptote. Shift left and right, I mean a horizontal line, it goes left and right forever. So if you shift it to the left, does it change anything? Nope. It's already to the left and to the right forever. So if I move it to the left or to the right, it doesn't really change anything. All right, how to solve exponential equations, right? Solving exponential equations. So I'm going to show you my best methods. Now I'll tell you, you'll probably try to do it some easier way. I know you will. You'll be tempted by the dark side, right? You'll be like, well, I can do it easier. Yeah, I know you can. But then when the problems become harder, can you? No, you can't. So when we start this, my advice to you is to do it the way I'm doing it. Think about it the way I'm trying to get you to think about it. Because if you think about it your way, there's a good likelihood that your way is not really the way, right? Most of the time, that's how it is, right? When someone who knows something is showing us and we're like, oh, yeah, I know this too. Nah, we think we know it, but we don't know it. I'm telling you, I know this. You might be telling me you think you know this, but I'm saying, maybe you do, but we'll see. All right, so let's look. Step 1. This is changing the base, right? So I'm going to call it changing bases. Changing bases. All right. Now, 81 and 1/3. When I'm doing this, I'm thinking about what? 81 and 1/3. Well, I should be thinking about 1/3 and really the 3. I don't want fractions. Nah, that's crazy. So let me change the base and make it not a fraction anymore. What if I say, instead of 1/3, what if I say 3 to the -1, right? Can I do that? Well, it's a +1 in the denominator. Can I move it to the numerator and make it a -1? Sure, I can do that. But everything else is still the same, right? 81. So now properties of exponents, right? So let's talk about these properties. I told you I'd talk about them when they become more relevant. So if I have a to the m to the n power, that is a to the m times n. All right, so this makes it 3 to the -x power equals 81. All right, that makes it 3 to the -1, or to the -x power. All right, now I got this base of 3. This is my base, right? base. Well, 81 right now is just 81. But can I represent it as 3 to some power? Well, I know, 9 times 9 is 81, and 3 times 3 is 9. So 3 to the 4th is 81. So this is 3 to the negative x power equals 3 to the 4th, right? Now, the purpose of changing our bases is to make the bases match. Bases match. When the bases match, think about this, right? Hey, 3 to the negative x power, 3 to some power is equal to 3 to the 4th power. Well, what does that mean? That must mean that this thing right here, this some power equals 4. So negative x equals 4, which means x equals negative 4. Bam. That's how you do it. All right. You're going to be tempted to go about it your easier way, but trust me. Don't do it yet. Wait till the whole story is revealed before you decide you know the ending. All right, let's keep rolling. So I would normally say, well, I guess I'll do another one, right? We'll go 76, right? So 5 to the 2 plus 2x power equals 25, all right? So I see that this is a base of 5. This is my base of 5. Now, this is 25. Can I express it as 5 to some power? Sure. I can say this is 5 squared. So 5 squared is equal to 5 to the 2 plus 2x. Now my bases match, right? Bases match. So 5 to some power equals 5 squared. That means this power right here must be the same as that right there. So 2 plus 2x must equal 2. Which, I subtract 2, I got 2x equals 0, therefore x equals 0. That means, if you think about this, 5 squared plus 2x, that means that had to be equal to 0 to equal 2. Yeah, that makes sense. All right. Let us keep it rolling. Here, solving an equation, right? So notice the problems are getting increasing in difficulty. But if you keep what I'm trying to tell you, right, and you keep it in your mind, then the problems don't become that much more difficult. I'll show you what I'm talking about. I got bases here. I got a base of 2 and a base of 8. Now, I want to change them to be the same. But I never want to take the smaller one and try to make it the larger one. Notice that every one that I've done so far, I'm taking the larger number and trying to make it the smaller number, right? I'm not trying to take the smaller number and make it the larger. No. Larger number to the smaller number. So I got 2 to the x plus 4 equals, and this is 8, right? This is 8 to the x minus 6. But I don't want it to be 8. I want it to be 2 to some power. Well, 8, right? 8 equals 2 to the 3rd. So I can say 2 to the 3rd to the x minus 6. And remember, if I got a to the m to the n, that's a to the m times n, right? So that means I have 2 to the x plus 4 equals 2 to the 3 times x minus 6. Oh, my bases match. Right? Now I can say, hey, this power must equal that. So x plus 4 equals 3 times x minus 6. I can distribute first and say this is 3x minus 18 equals x plus 4, subtract x plus 18 plus 18. So I got 22 equals 2. x. Therefore, x equals 11. Boom, 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 boom. Right? That wasn't so bad. It looks like it's going to be bad, but if you keep the technique in your mind, it's not so bad. We'll do an example. Maybe I'll do 2 examples. I'm when I'm looking at this one over here, I focus in on these fractions because I know how, people be intimidated by fractions. Let's do this 74 real quick. I got 2/3 to the x power equals 9/4. Now, I should be able to look at this and kind of tell, the 3 could be a 9 and the 2 could be a 4. All right, so let's change that. I got 2/3 to the, and maybe, there's a lot of different, strategies you can do. But remember, so my 2 is in the numerator, my 3 is in the denominator, but my 9's in the numerator and my 4 is in the denominator. So I can say this is, I can say this is 3/2 squared, right? 3/2 squared is the same as 9/4. But this is a 2/3 x, so it doesn't match yet. They're not the same. But if I make one of the exponents, whichever one you prefer, negative, then it flips. I'm gonna make my x negative, and when I do that, it becomes 3/2 to the negative x equals 3/2 squared. Haha, the bases match. So I can say, hey, negative x equals 2, so x equals -2. Bam. All right, that was just, I saw that and said, let's do one of these 2. Let's go with, I'm going to do this one, 79. So 27 to the 4x is equal to 9 to the x plus 1. All right. 27 and 9. Can I express 27 as 9 to some power? No, I can. I can, but not a regular power. Like it would be like a half power or like a decimal power, which I don't want to get into that because that's confusing. But I do know 27 is 3 cubed and 9 is 3 squared. So 3 cubed equals 27. 3 squared equals 9. Ooh, so 3 is my link here. So, and you should be able to see that, that you should see that that's both powers of 3. So this is 3 cubed, right, to the 4x equals 3 squared to the x plus 1. Then we got that power rule. So this is 3 to the 12x equals 3 to the 2 times x plus 1. Well, my bases match, right? These match. So I know I'm ready for that. When my bases match, I can, 12x equals 2 times x plus 1. The 2 distribute. That's 2x plus 2 equal 12x. Subtract 2x, subtract 2x. I got 10x equals 2. So x equals 2/10, right? Which is 1/5. I'm saying, now, if you're that person that's been doing it in your mind, or, there's always that person. If you're that guy, I doubt you would have been on that one. I'm just saying. Or lady, if you were that person, you probably would have got that one wrong. Probably would have got a couple more of these wrong. But that's what I'm saying. Don't try to find a different way. That's what people always try to do in math. They want to be the first to discover some, glory. I'm going to get the glory. Yo, there ain't no glory in this. There is, but, you might get it, but it ain't going to be here. I don't know. It could be. Keep striving for glory, friend. but just go the path I'm telling you so you can actually get the answers. All right. What about this one? So this is kind of a different strategy. Notice that the x is not in the exponent position. So this is like a different type of problem. On all these other ones that I was just showing you, x is in the exponent position, right? That's how it was going down. But in all of them, but on this one, x is not in the exponent position. So x to the 4/3 power equals 81. Here's how you would handle this. Or this is how I handle it. You can handle it different ways, but I prefer this way because it makes sense to me. And you want math to make sense to you, because if not, it's just a bunch of formulas. So if I have x to the 4/3 power, I could rewrite that as the cube root of x to the 4th. And that equals 81. All right. And now I'm thinking, what can I do to get x by itself? Well, I got to undo the things that's happening to it, right? So first, I'm going to just say it's being cubed. Or cube root, excuse me. It's the cube root. Well, what's the opposite of the cube root? The opposite of the cube root is a cube. What I do to one side, I do to the other side. Cube. The cube and the cube root cancel out, and I have x to the 4th equals 81 cubed. Now, I'm not going to bother with that. I'm probably going to have to at some point. But for now, I'm just going to say, what can I do to get x by itself? All right. Well, x is being fourthed, right? X is the 4th power. I need the 4th root. 4th root. That means that cancels. And here is, anytime you do a 4th root, you should honestly anytime you do an even root, you got to do a plus or minus, but this is the 4th root of 81 cubed, which means x is going to equal that. I'll put it in my calculator, see if it gives us a nice answer. If it gives us something that's exact, we'll use it, and if it gives us something that's approximate, we'll get the exact answer by hand. So I feel like it would be exact. So if you got a TI-84, you hit math first and you go down to the 5th one and you'll see the x root, and then you need to put a 4 in there. So the 4th root of, and then you say 81, and then under the clear button there's that, it's called a caret, but it just looks like an arrow pointing up a little bit. That gives you the exponent of 3. You put that in and it tells us 27. So my answer would be plus or minus 27. All right. So we'll do another one of these. I guess we'll do 85. 85. So we got x to the 5/2 equals 32. X to the 5/2 equals 32. I'm going to rewrite it first. So this is the square root of x to the 5th equals 32. All right. And then first I get rid of the square. So I do the opposite of a square, I do the opposite of a square root, which is a square. The square and the square root cancel out, and I got x to the 5th. I have to do the same thing to both sides. Right, so that equals 32 squared. I'm not going to worry about figuring out what that is yet. Then I do the opposite of a 5th. Opposite of the 5th power is the 5th root. Whatever I do to one side, I do to the other. The 5th root and the 5th power cancel out. And then over here, if I take the 5th power, it's an odd, if I take the 5th root, it's an odd root. I don't have to consider a plus or a minus. It's always going to be, the answer is not or, the answer is just that. So it's just one of those. It's not going to be plus or minus. It's just the plus in this case because we got positive 32. So the 5th root of 32 squared. So I'm going to put that in my calculator. You hit math, scroll down to number 5, and you'll see x root. You make sure it says the 5th root, and then you say 32, the caret key, square, and we get this answer is 4. So it's just 4. It's not plus or minus 4, it's just 4.